Now we have defined our three segments and we have added them and they are well defined, but still the pipe segment is not able to solve here because we have heat transfer information under defined. Again, when I was here as the parameters, I mentioned that we have a duty because we have entered a heat stream. So now we are under specified. So how to solve this problem? From rating, you can go to heat transfer. Okay, you can add the heat loss if you have over all heat transfer coefficient. Here you can have it. Okay, if you have any information about the total, this is the total heat transfer, and this is for the segment because we have three segments. If you have the ambient temperature of each one and the heat transfer coefficient of each one. In this case, I don't have any information about the heat transfer, so I'm going to estimate it. Here, we don't have any information about the insulation. We are sure that we have a pipe wall, so we are going to include it. We have an inner heat transfer coefficient, so we are going to include it. And I haven't mentioned anything about the insulation, so we are not insulating this pipe, so we will keep it unchecked. And we are going to check the outer heat transfer coefficient. Okay, so this is how we estimate the heat transfer coefficient. And here you have ambient temperature, we enter it to be 5. Okay, so here we are using the global, not by segment. We are defining the global, the total. Okay, if you choose by segment, you have 3 printed results for the 3 segments that we have. Okay, so now after adding this information about the heat transfer here, the estimate HTC, we will find out that our pipe segment is solved. Okay, so now let's answer this question. What is the outlet pressure of our branch? Okay, so outlet pressure here, what is its value? So you can know it from here. Double click and you will find the P1 out or branch 1 out. The pressure in kilopascal is 3891. Okay, there is another method to find out. As the branch here, you can go to the worksheet and the pressure out will be displayed here. Okay, through the performance you will have the distance in meter. So these are the distance and this is the elevation, and this is, you have 5 increments for each one because here we are dealing with two phases only. So you can have a pipeline with 1 phase flow, 2 phase flow, or 3 phase flow. The number of phases when increased, like for example, if you have this stream, it's only gas and oil or gas and liquid. So in this case, the stream increment or will be divided into 5. Okay, but if you have 3 phases, you need to increase this number, and I'll show this one for you in the branch number 3. Okay, the same way we did for gas well number 1, we are going to do for gas well number 2. So in this case, we are going to add another pipe segment, but this time for the second well, and this branch will be divided into 2 segments only, not 3. Okay, so branch number 2, and the inlet will be the produced from gas well number 2, and here it will be branch number 2 out. Okay, and we need to add an energy stream, which is P2 out, Q. This is for the energy. You haven't added any segment, so now you are going to go to the rating and the sizing, and you are going to add 2 segments. Okay, add them. So both of them will be pipe, and the elevation or the length. Let's add the length at the beginning. The length of the first one will be 200 meters, and the elevation will be 23 meters. And the nominal diameter, you remember how we added the nominal diameter? You go to view the segment, we agreed on schedule 40, and our nominal diameter we will choose 100 millimeter. Okay, so the nominal diameter here is higher than the one of the branch number 1. Okay, also we need here to add our correlation. We haven't changed the correlation, so after the connection go directly to the parameter, and again here we have 2 phases, only gas and liquid, So we are going to choose a two-phase Tulsa unified model, okay, for the 3. And this is our last one, okay. So we have checked our correlation here. So for the rating, we have added our information, double check. Yes, we choose it. For here pipe, for the segment number 2, we have information that the segment number 2, in this case, there is only information available for one segment, so we are going to delete this one. Okay, so we have this information available. Now it's time to add the heat transfer information. So we are going to estimate it, and again, this will be 5 degrees Celsius. We include the pipe wall, include the inner HTC and outer HTC. Okay, now it will be fine. Here I want to check the composition of this gas well. The composition here, we will find water. There should be water here. Okay, that's why we have a two-phase here. It's the 3-phase, sorry. This one is the gas, this is the second phase water, and the third phase, this is our oil or the liquid. Okay, for gas well 1 and D2, if you check the composition, so this is our gas well number 2, the composition, you will find that the water composition equal to 0. That's why I mentioned it's a 2-phase. So now we are going to work with a 3-phase. Okay, so we are going to add a pipe segment here, and this one will be our third branch. This is our branch 3. The inlet will be the one from the third well, and the outlet will be P3 out, and we have a P3 energy 2 for the heat losses energy, or Q. Okay, so after that we go to our parameter, and this time we are going to change the correlation to Tulsa unified model, but in this case there are 3 phases. Okay, be careful with the number of phases because this is really important. The addition of one new phase will affect the number of increments that we are going to use later. Okay, so we have added this information. This sizing, the rating, the sizing, we have information for 3 segments. So we are going to create 1, 2, 3 segments. All of these will be a pipe. The first one length is 160, and its elevation is 12.2 meters. So it's really high in the earth, and above the ground. So we have a nominal diameter. We will view the segment, and it's important to finish each segment separately. Okay, it's 40, schedule 40, and we have 80. Again, we return back to 80 millimeter. Okay, for the second one, we have a length of 99, and it's buried under the ground negative 14 meter. And also we have to view the segment here. To the actual here will be schedule number 14, and we have a nominal diameter of 80 millimeter. 80 millimeter. Okay, for the third one, we have a length of 204, and it's also under the ground, so it's negative 0.9 meter, and we need to view the segment to change the schedule. Don't forget this step because this is important. Okay, and we are going to add 80 millimeter. Okay, now we still have a problem with the heat transfer, so I don't have information, so I'm going to estimate it. And in this case, I'm going to add 5 degrees Celsius for ambient temperature, and I'm going to include the pipe, include the inner HTC, and include the outer HTC. Okay, as I mentioned before, the number of incrementation, or the number of increments that I'm dividing each segment to it must be increased. Okay, so instead of 5, this is the default, I'm going to increase it to 10. How to find this one? From rating, go to sizing again, and the number of increment here, we are going to increase it to 10 for each one, because here we are dealing with 3 phase, so it will be much easier. So if you are dealing with a 3 phase, this will be much easier to calculate the 3 phase flashes here. Okay, along with the length. So we have increased it from 5 to 10. Okay, here it's mentioned there is no enough information for the pipe calculation because, as if you remember, this stream is not well defined. So if you entered all the information during maybe the exam or during the work and it is still not defined, it's okay. Maybe something you are going to add later will define or back define it. Okay, so now we are going to add a mixer and we are going to mix our two streams. Okay, here I'll work with this one again, but here as we are saying, this one is not defined because this stream is not defined. So this one would be also the same case. So in this case, I'm going to work with these two streams that I'm already defined. Okay, so in this case, I'm going to mix them together. So this is our mixer, and double click to open it. We have this mixer. Maybe we call it mixer or junction 1, so G1 or junction 1. And in this case, I'm going to mix two streams, the out from B1 and the out of B2. Okay, remember you are mixing the two material stream, not the energy stream. So this is the G1 or the junction 1 out, and here we have mixed them. Okay, for the parameters here, sometimes you can equalize all or set the outlet to the lowest inlet, which means here the pressures will be equalized, all the pressures will be equalized. But this one, you have this pressure is 10 psi and this one is 20, so it would be set to the lowest, which is 10 psi. Okay, we have our mixer here and we have this stream is well defined. So I have mixed the product of the two streams and I'll have a temperature of 36. This is a pressure, this is the lowest pressure. So it chooses the lowest one. Okay. Now I'm going to define our branch, our last branch, this one, branch number 4.